Ice, in its varied forms, covers as much as 16% of Earth's surface, including 33% of land areas at the height of the northern winter. Glaciers, sea ice, permafrost, ice sheets, and snow play an important role in Earth's climate. They reflect energy back to space, shape ocean currents, and spawn weather patterns. But there are signs that Earth's great stores of ice are beginning to melt. To find out where Earth might be headed, scientists are drilling down into the ice and scouring ancient seabeds for evidence of past climate change. What are they learning about the fate of our planet 1,000 years into the future and even beyond? "30,000 years ago, Earth began a relentless descent into winter. Glaciers pushed into what were temperate zones. Ice spread beyond polar seas. New layers of ice accumulated on the vast frozen plateau of Greenland. At 3 kilometers thick, Greenland's ice sheet is a monumental formation built over successive ice ages and millions of years. It's so heavy that it has pushed much of the island down below sea level. And yet today, scientists have begun to wonder how resilient this ice sheet really is. Average global temperatures have risen about 1 degree Celsius since the Industrial Revolution. They could go up another degree by the end of this century. If Greenland's ice sheet were to melt, sea levels would rise by over 7 meters. That would destroy or threaten the homes and livelihoods of up to 1/4 of the world's population. These elevation maps show some of the areas at risk. Black and red are less than 10 meters above current sea level. The southeastern United States, including Florida and Louisiana, Bangladesh, the Persian Gulf, parts of Southeast Asia and China. That's just the beginning. With so much at stake, scientists are monitoring Earth's frozen zones with satellites, radar flights, and expeditions to drill deep into ice sheets. And they're reconstructing past climates, looking for clues to where Earth might now be headed. Not just centuries, but thousands of years in the future. Periods of melting and freezing, it turns out, are central events in our planet's history. That's been borne out by evidence ranging from geological traces of past sea levels, the distribution of fossils, chemical traces that correspond to ocean temperatures, and more. Going back over 2 billion years, Earth has experienced 5 major glacial or ice ages. The first, called the Huronian, has been linked to the rise of photosynthesis in primitive organisms. They began to take in carbon dioxide, an important greenhouse gas. That decreased the amount of solar energy trapped by the atmosphere, sending Earth into a deep freeze. The second major ice age began 580 million years ago. It was so severe, it's often referred to as Snowball Earth. The Andean Saharan and the Karoo ice ages began 460 and 360 million years ago. Finally, there's the Quaternary, from 2.6 million years ago to the present. Periods of cooling and warming have been spurred by a range of interlocking factors. Volcanic events, the evolution of plants and animals, patterns of ocean circulation, the movement of continents. The world as we know it was beginning to take shape in the period from 90 to 50 million years ago. The continents were moving toward their present positions. The Americas separated from Europe and Africa. India headed toward a merger with Asia. The world was getting warmer. Temperatures spiked roughly 55 million years ago, going up about 5 degrees Celsius in just a few thousand years. CO2 levels rose to about 1,000 parts per million, compared to 280 in pre-industrial times and 390 today. But the stage was set for a major cool down. The configuration of land masses had cut the Arctic off from the wider oceans. That allowed a layer of fresh water to settle over it, and a sea plant called azolla to spread widely. In a year, it can soak up as much as 6 tons of CO2 per acre. Plowing into Asia, the Indian subcontinent caused the mighty Himalayan mountains to rise up. In a process called weathering, rainfall interacting with exposed rock began to draw more CO2 from the atmosphere, washing it into the sea. Temperatures steadily dropped. By around 33 million years ago, South America had separated from Antarctica. Currents swirling around the continent isolated it from warm waters to the north. An ice sheet formed. In time, with temperatures and CO2 levels continuing to fall, the door was open for a more subtle climate driver. It was first described by the 19th century Serbian scientist Milutin Milankovic. He saw that periodic variations in Earth's rotational motion altered the amount of solar radiation striking the poles. In combination, every 100,000 years or so, these variations have sent Earth into a period of cool temperatures and spreading ice. Each glacial period was followed by an interglacial period in which temperatures rose and the ice retreated. The Milankovic cycles are not strong enough by themselves to cause the shift. What they do is get the ball rolling. A decrease in solar energy hitting the Arctic allows sea ice to form in winter and remain over summer. Then to expand its reach the following year. The ice reflects more solar energy back to space. A colder ocean stores more CO2, which further dampens the greenhouse effect. Conversely, when ocean temperatures rise, more CO2 escapes into the atmosphere, where it traps more solar energy. With so many factors at play, each swing of the climate pendulum has produced its own unique conditions. Take, for example, the last interglacial, known as the Eemian, from 130 to 115,000 years ago. This happened at a time when CO2 was at pre-industrial levels, and global temperatures had risen only modestly. But with higher solar energy striking the north, temperatures rose dramatically in the Arctic. The effect was amplified by the lower reflectivity of ice-free seas and spreading northern forests. There is still uncertainty about how much these changes affected sea levels. Estimates range from 5 to 9 meters, levels that would be catastrophic today. That's one reason scientists today are intensively monitoring Earth's frozen zones, including the ice sheet that covers Greenland. Satellite radar shows the flow of ice from the interior of the island and into glaciers. In the eastern part of the island, glaciers push slowly through complex coastal terrain. In areas of higher snowfall in the northwest and west, the ice speeds up by a factor of 10. The landscape channels the ice into many small glaciers that flow straight down to the sea. In the distant past, the center of the island may have been drained by a giant canyon, recently discovered. Scientists found that it's 550 kilometers long and up to 800 meters deep. It leads from Greenland's interior to one of today's most volatile glaciers. This is the Petermann Glacier in northwest Greenland. Amid unusually warm summer temperatures in 2012, satellites tracked a giant iceberg as it broke off and moved down the glacier's outlet channel. At about 31 square kilometers, this island of ice stayed together as it floated along. After 2 months, it finally began to fragment. The Jakobshavn Glacier on Greenland's west coast flows toward the sea at a rapid rate of 20 to 40 meters per day. At the ice front, where the glacier meets the sea, Jakobshavn has been retreating as it dumps more and more ice into the ocean. You can see it in this map. In 1851, the front was down here. Now it's 50 kilometers up. One reason, scientists say, is that water seeping down into its base is acting like a lubricant. Another is that as the glacier thins, it's more likely to break off or calve when it interacts with warmer ocean waters. Scientists are tracking the overall rate of ice loss with the GRACE satellite. They found that from 2003 to 2009, Greenland lost about 1 trillion tons, mostly along its coastlines. This number mirrors ice loss in the Arctic as a whole. By 2012, summer sea ice coverage had fallen to a little more than half of what it was in the year 1980. While the ice rebounded in 2013, the coverage was still well below the average of the last 3 decades. Analyzing global data from GRACE, one study reports that Earth lost about 4,000 cubic kilometers of ice in the decade leading up to 2012. Sea levels around the world are now expected to rise about 1 meter by the end of the century. What will happen beyond that? To gauge the resilience of Greenland's great ice sheet, scientists mounted one of the most intensive glacial drilling projects to date, the North Greenland Eemian Ice Drilling Project, or NEEM. The ice samples they obtained from the height of the Eemian warming told a surprising story. If you were a visitor to northern Greenland in those times, you would have stood on ice over 2 kilometers thick. Temperatures were warmer than today by about 8 degrees Celsius, and yet the ice had receded by only about 25%, a relatively modest amount. This has shifted the focus to Earth's other much larger ice sheet, on the continent of Antarctica. Antarctica contains 90% of all the ice and 70% of all the fresh water on the Earth. Scientists are asking, how dynamic are its ice sheets? How sensitive are they to melting? Data from GRACE and other satellites shows that this frozen continent overall has lately been losing as much ice as it gains. The vast plateau of Antarctic ice is one of the driest deserts on Earth. What little snow falls remains, adding to the continent's mass. You can see evidence of this in the snow and ice that piles up at the South Pole Research Station. This geodesic dome was built in the 1970s. By the time it was decommissioned in 2009, the entrance was nearly buried. With a thickness of up to 4 kilometers, the ice on which this outpost sits will not melt easily. That's true in part because of the landmass below it, captured in an extraordinary radar image. The eastern part of the continent, the far side of the image, is a stable foundation of continental crust. In contrast, the western side dips as much as 2,500 meters below present-day sea level. Along the Amundsen seacoast, the ice is disappearing at an accelerating rate. Inland ice streams are moving toward the ocean at least 100 meters per year. They end up in floating ice shelves that extend hundreds of miles into the ocean. This is the Pine Island Glacier, a major area of focus for researchers investigating the impact of a warming climate. This region is the greatest source of uncertainty about global sea level projections. When ice shelves like this grow, they become prone to fracturing. A giant crack, for example, recently appeared in the Pine Island Glacier. Within 2 years, a 720 square kilometer iceberg had broken off. But the scientists are more concerned about what's happening below the surface. In recent times, the Southern Ocean that swirls around the continent has been getting warmer, at the rate of 0.2 degrees Celsius per decade. That has affected ice shelves like Pine Island by melting them from below. In a comprehensive survey of the continent, scientists concluded that this process was responsible for 55% of the mass lost from ice shelves between 2003 and 2008. It's also been blamed for one of the more puzzling twists in the story of climate change: the spread of sea ice all around Antarctica. One possibility is that ramped-up winds circling the pole are pushing the ice into thicker, more resilient formations. Another is that the melting of ice shelves has spread a layer of cold, fresh water over coastal seas, which readily freezes. A team of researchers has come to the Pine Island Glacier to try to monitor the melting in real time. After 5 years of preparation, they drilled through 500 meters of ice to begin measuring ice volume, temperature, salinity, and flow. In some places, they found melt rates of about 6 centimeters per day, or about 22 meters in a year. Because ice shelves hold back inland glaciers, the melting could trigger larger changes. That's likely what happened to the Larsen ice shelf on the Antarctic Peninsula in the year 2002. It's thought to have been stable since the last interglacial. Warmer ocean waters had been eating away at Larsen's underside. By early February of 2002, the shelf began to splinter into countless small icebergs. By March 7th, when this picture was taken, it had completely collapsed, forming a vast slush that drifted out to sea. Without the shelf's buttressing effect, a series of nearby glaciers picked up speed, dumping an additional 27 cubic kilometers of ice into the ocean per year. Evidence from the last interglacial, the Eemian, brings an ominous warning of what could lie ahead. It's based on the height of ancient coral reefs, which grow to a depth relative to the sea level above them. Based on reefs along the Australian coast, a recent study published in the journal Nature showed that sea levels remained stable for most of the Eemian, at 3 to 4 meters above those of today. But the authors found that in the last few thousand years of the period, starting around 118,000 years ago, sea levels suddenly shot up to 9 meters above today. The authors concluded, in their words, that a critical ice sheet stability threshold was crossed, resulting in the catastrophic collapse of polar ice sheets. Looking ahead, uncertainties about the future of our climate abound. According to one study, the long cool down to the next glacial period is due to start in the next 1,500 years or so, based on the timing of Milankovitch cycles. But for that to actually happen, the study says, enough new ice would have to form to jumpstart the new glacial period. And CO2 would have to retreat to below pre-industrial levels. Instead, it appears that a warming climate is becoming a fact of life. The danger is that if the melting gains a momentum of its own, even reducing CO2 emissions may not be enough to stop it. The still unfolding story of Earth's past tells us about the mechanisms that can shape our climate. But it's the unique conditions of our time that will determine sea levels, ice coverage, and temperatures. What's at stake in the coming centuries is the world we know, the one that has nurtured and sustained us. The Earth